This is Anthony Pham, an up-and-coming triathlete. His journey started off fairly slow, but since then, he has made progress through the ranks and recently won the Ironman World Championship. However, his remarkable growth has sparked doping allegations. Recently, officials confiscated a bag of his rocket fuel. Despite the odds being stacked against him, Anthony pleads his innocence. Doping? What the? Let me call my manager.
Hello.
Boss, I need your help.
Hey Anthony, what's up?
Boss, I've been accused of doping. I need you to help out.
Oh, no worries. I'll call the best scientist I know. Let me call Ella. Hey Alex, what's up?
Hey, so there have been some reports that my athlete Anthony has been doping. So I need to get you on this to figure out what's going on. They confiscated a sample of something from his bag called rocket fuel. So what do we need to do?
Okay, I'm gonna need you to send me a couple samples. I'm gonna need urine, blood, and then if he has some remaining rocket fuel, that would be great.
Okay, awesome. I'm on it. Thanks, Ella.
Yeah, you're welcome.
I can't have this happen to me.
Hey Pham.
Oh, hey.
Hey, how's it going?
I'm trying to hang in there.
I know it's gonna be okay. I just got off the phone with Ella and she said that we need some samples. Okay, so
Okay,
we
what
need
kinds?
a urine sample and we need a blood sample. Now, luckily, I'm a phlebotomist, so that blood sample will be easy.
Blood?
Yeah, just gotta get some blood samples. No worries, no worries. Pham, are you okay? Hey, you're all good. We got the samples, so that's good news. You don't have to worry about it.
Wait, what?
You feel okay?
I feel a little dizzy.
Yeah, that's all right. When you're ready to go, we also need a urine sample. So when you can do that, that'd be awesome.
Hey boss, got your urine samples here.
Okay, perfect. I'll send this off to Ella, and we'll be all set.
Yeah, fingers crossed.
Yes.
Hey, these came in the mail for you.
Thank you. This should be Anthony's samples, but let's check. Okay, perfect. Now we can start sample prep in order to analyze these with gas chromatography, mass spectrometry, and powder X-ray diffraction.
In either case, make sure the athlete splits the sample into 2 equal containers. The A sample will be used in initial testing, and the B sample will be used as a backup should the A sample come back positive. This ensures accuracy and reproducibility. Gas chromatography is a powerful technique that is routinely used for the screening of doping control samples on the misuse of performance enhancement drugs. This is the most effective and frequently used method for its speed and high throughput, which allows for faster reporting times and cheaper instrumental costs. It's also extremely versatile as multiple internal standards can be used for analysis. To analyze these samples, first insert the P into the machine. For urine, we extract the volatile components via liquid-liquid extraction with an organic solvent. Then, concentrate the samples with a rotary evaporator. For blood samples, centrifuge the samples to separate the plasma or serum. Afterwards, precipitate the proteins via the addition of an organic solvent such as methanol and centrifuge again to collect the supernatant containing the analytes. Then, perform liquid-liquid extraction like the urine to isolate the targeted compounds and evaporate. Now, the samples are ready to be analyzed. When the samples are injected into the machine, the oven inside instantly vaporizes said samples into a gas. Afterwards, the carrier gas, such as helium, sweeps the vaporized samples into the gas chromatography column. The column is where the compounds are separated based off of their chemical properties. The more volatile compounds move faster, whereas the other ones are retained longer. As the compounds exit the column at different times, the detector measures the compounds, providing a signal to make a chromatogram. The chromatogram compares the retention time with the signal intensity. Also in the detector, the vaporized samples are analyzed in tandem with a mass spectrometer.
Mass spectrometry is being used tandem with our gas chromatography machine in the case of the possible doping incident. The gas chromatographer turns our sample into gaseous form, and this gaseous form is required for analysis on the mass spectrometer. Mass spectrometry generally works by producing an ion fragment of the gaseous molecule being examined by bombarding it with energy, then examining the mass-to-charge ratio of the fragments produced by ionization. This is descriptive of the molecular mass of the compound because all of the charges which are created from mass spectrometry are generally +1, leading to the output being a direct readout of the mass of the molecule in question. Ion sources and mass analyzers can vary, and there are multiple types of each which can be easily described. A mass spectrometer is an extremely fast, specific, and selective piece of equipment, as the fragmentation patterns are like the thumbprint of the molecule, and one is able to derive the structure of the molecule using mass spectrometry. There are two major types of ion sources, gas phase and desorption sources. Since we are going to be using molecules already in the gaseous form, I will describe a few of these types of ion sources. The common gaseous ion sources include electron ionization, chemical ionization, and matrix-assisted laser desorption ionization, which is usually paired with a time-of-flight mass analyzer. In electron ionization, the electron source is usually a heated tungsten filament which emits electrons. These electrons are then accelerated by an electrical current and collide with the molecule at a right angle to ionize it. About 1 in a million molecules will undergo this ionization, and this is a rather hard source for ions. While generating ions for a mass spectrometer, there is also a vacuum system hooked up, which ensures that there is minimal ion collisions, hopefully increasing the overall number of ions produced. The ions are then accelerated and focused into a beam for shooting at the mass analyzer. After ionization by an ion source, the fragmented molecule passes through a mass selector, in which the molecules are separated based on their mass-to-charge ratio. Since the charge on the molecule after ionization is usually +1, it can be said that the molecules are separated by mass. Three commonly used mass analyzers are the electromagnetic sector, the quadrupole, and the time of flight. The electromagnetic sector and the quadrupole are considered scanning analyzers, while the TOF is a simultaneous transmission analyzer. The quadrupole is formed by 4 electrode cylinders which have alternating charges so that there is a positive charge and a negative charge on a pair of cylinders. These pairs have an applied radio frequency and DC voltage which can be changed. This mass analyzer works by accelerating ions through the quadrupole while the DC voltages on the rods are changed. This causes the ions except those with a specific mass-to-charge ratio to hit the rods, where they are converted to neutral molecules. The ions which pass through are effectively separated and moved to the ion transducer, which converts the ion kinetic energy into a mass recording. This selector is less expensive and more compact and can generate entire mass spectra very quickly, so it is generally preferred over the electromagnetic sector. There are a few different detectors for mass spectrometry, including the Faraday cup and the electron multiplier detector. The latter method is generally higher resolution and functions similar to a photomultiplier tube. A mass spectrum is generated by the machine readout, and this can be examined to determine the molecular mass of the unknown compound and the general structure by the fragmentation pattern of the molecule. In the case of the doping sample, we will be examining the molecular mass of the makeup of chemicals in the blood and matching this with a library of known molecular fragmentation patterns. We will be looking for substances not expected to be found in the blood to give us a clue of any doping which might be happening with our star athlete.
The first step in powder X-ray diffraction, or PXRD analysis, is sample preparation. A crystalline sample must be ground into a homogeneous powder. Homogeneous samples are samples that have the composition the same everywhere throughout it. A good example of this would be a Hershey's bar. A heterogeneous sample, on the other hand, has a material composition that differs from region to region. A good example of this in our candy bar situation would be a Crunch bar. This homogeneous powder is then usually placed within a sample holder that contains a divot. The holder is packed tightly with sample crystals in every possible orientation. The sample holders can be made out of aluminum, bronze, bakelite, or glass. Powder X-ray diffraction, or PXRD, is one of the most important methods for determining the structure of complex products such as steroids, vitamins, and antibiotics. It allows for the qualitative and quantitative analysis of solid samples. When an X-ray beam is placed on a powder, a diffraction pattern specific to that material is produced. PXRD is often simpler and easier to use than single crystal diffraction due to it not requiring individual crystals to be formed. Diffraction patterns plot intensity versus the angle of the detector in 2 theta. The overall diffraction pattern is similar to how grates work in other instruments, including UV-Vis, with diffraction grating being the best dispersing element in this instrument. It also follows Bragg's law in the same way that grates do. The instrument is composed of an X-ray source, a sample stage, an X-ray detector, and a way to vary the angle. The detectors are often made of transducers that produce an electrical signal. The diffraction pattern is then matched with a known database to determine if the steroids of interest are present.
That's odd. The sample isn't showing any signs of doping, but it looks as though the rocket fuel is actually lead sulfate, which is highly toxic. It looks as though someone's trying to poison Anthony. I need to call Alex immediately.
999.
Hey,
What
Pam.
is it? Oh,
Hey.
what's up?
Hey, I got a call from Ella, okay? So she said the lab results came back, and I have good news and bad news. Good news is your sample didn't show up for any doping. Doping chemicals. So we've ruled that out. You're not doping. Bad news is lead sulfate showed up, and that means that somebody is trying to poison you, is what they think. So we have to get the authorities involved to investigate. Yeah, so. I'm sorry, I know that's shocking.
No wonder why I haven't been able to train lately. I think we're gonna have to fire our nutrition sponsor. And there you have it. Both Anthony's A and B sample came out negative. This means that Anthony is a clean athlete. Next, inform the race organizations the results of the doping test. Anthony is now free to pursue his next triathlon. Let Anthony's experience show you why there's a need for anti-doping. Not only does it provide a clean and fair sport, but it also shows you the practicalities of the instruments taught in instrumental analysis and analytical chemistry. Now there's only one question remaining. Who was trying to poison Anthony? I guess we'll never know. Wait a minute. This is coming in. It appears they have found the suspect.